All right, real quick video to end up this little subunit on entropy. Now, with thermodynamics, I usually think about it, I do think about it in three subcategories. I think about thermodynamics in terms of enthalpy, nailed it, did that. In terms of entropy, doing it now, about to nail that. And then last but not least, what's called Gibbs energy or Gibbs free energy. And that's a third subunit of the thermal unit. So let's wrap up the second subunit here with a real quick video, hopefully this time. I know, because you get so tired of seeing me and listening to me battling on. All right, last problem here on this side. We have state weather, number 6. State weather, the sign of the entropy can be expected. So we're going to make a prediction here. You now know enough about entropy, hopefully, that you can predict whether or not a reaction will become positive entropy or negative entropy, increased disorder or decreased disorder. You should be able to figure that out by looking at a reaction. Let's see if we can do it. Indicate whether or not the following processes will be positive or negative entropy and explain your prediction. So with A, we have PCl3. Okay, I hope you got this because I'm not writing these down. Okay, you got this in front of you. I don't have to write it down. Okay, I don't have to do your work for you. Okay, I'm not your mom. Okay. All right. PCl3 liquid plus Cl2 gas makes PCl5 solid. So we've got the phosphorus trichloride and some chlorine gas going to make phosphorus pentachloride. Is that going to increase or decrease entropy? How do you know? Well, you went from a liquid and a gas. Gas is really disorganized. Liquid's kind of disorganized. Solid, not disorganized. Organized. Organized means less entropic. So on the right, the solid has more organization to it, so it's less entropy on the right and more entropy on the left. So what happens to entropy in this case? The entropy goes from disorganized stuff on the left to organized stuff on the right. So the entropy went down. The entropy, or disorganization, remember, that's kind of weird to get used to, but the entropy or the disorganization decreased because we got more organized. So it's a negative entropy. We lost disorganization. We lost entropy. All right, take a look at B. We have a solid, a liquid, or a solid on the left becoming a gas and a liquid. Well, that's just the opposite of the last one then. We have a solid, organized, going to a liquid, kind of disorganized, to a gas, really disorganized. So we went from organized to disorganized. That's the way nature likes things. It likes it. Nature likes that. So more disorganization, more entropy. Our entropy increased. That should be a positive or an increase in entropy. C, we have a gas going to a gas. Ooh, tricky. So we have hydrogen, diatomic hydrogen. Okay, it's breaking down to form 2 hydrogens. So here you have hydrogen and hydrogen. So which one is going to be more disorganized? Come on, you can do this. Here I have 1 molecule. I've broken that down into 2 atoms. 1 molecule, those hydrogens are locked together. They're bonded together. There's not too much freedom there. They're like bonded together. They can't do anything. Yeah, they're just kind of locked together, can't do anything. Kind of like being married. That's funny. Just kidding, honey. And here we have 2 individual hydrogen atoms. There's more freedom there. So this is going to be more disorganized than that. So the entropy here, or disorganization, should have gone up, or the freedom or the possibilities of the microstates, all those words, lumping them together, we increased our entropy. So it should be a positive value for C. D, we have a solid and a gas going to a solid. A solid and a gas going to a solid. Well, a solid becomes a solid, and you might say, based upon earlier, we have uranium solid. Now, this is going, what are we hooking it up with? 3 fluorines. So I'm going to get uranium hexafluoride. So I got my uranium, and that's a solid, gas, and solid. Well, you might say, well, this Actually, you might not, you shouldn't say, well, anything. We should just say for two reasons why this is going to be less entropy. Okay, less entropy. Why? Because it's a solid, and here you have a solid and a gas. You have a gas. That's wild and crazy. That is butt tons of disorganization, just butt tons of it. And so here you have a solid. Yeah, but here you have a solid as well. So now this solid compared to this solid compared to this solid, like we were talking about earlier, that should be more entropy than that. That's true. It should be more entropy than that, but the gas far and away makes up for a lot more. There's a lot more entropy in that gas. So because we went from really disorganized and not too disorganized to not too disorganized either, we actually decreased our entropy. We went down in entropy. It's a negative entropy. We become more organized because we got rid of that gas. Okay, now I'm going to give you an example, a little bit more of an example. This is a thinking thing. This would be good for a pre-response. Short answer question. A short answer question for you. Okay, here's a good short answer question. See if you can answer it. Beaker of water. Not just any old water, salt water. So you've got some sodium ions floating around in there, chlorine ions floating around in there, salt water. You put it outside on a table on a hot, sunny day. Sun, Mr. Golden Sun, shining down on me. All right, there's the sun. Sun's got sunglasses on, protect those eyes. And radiant energy, you know what's going to happen. That water is going to evaporate. And eventually it evaporates right down, and all you're going to be left with is what? That's right, salt crystals. You'll be left back with your sodium chloride crystals in that container. And we all know that sodium chloride is very awesome organized stuff because sodium chloride crystals are perfect little cubes. It's pretty cool. So we just went from highly disorganized. We had liquid water with sodium ions and chlorine ions floating around. Now, it's pretty disordered. It's not as disordered as a gas, but it's still pretty disordered. To solid, organized crystals. Does that not break the second law of thermodynamics? Does that not go from a more disorganized system to an organized system? Sounds to me like we're violating the second law of thermodynamics and we're going from a less ordered to more ordered. Oh, really? Are we? Okay, first of all, think about it. It's second law of thermodynamics. So you're thinking probably wrong. Okay, Einstein, you're probably not thinking correctly. You're missing the point here. Something's going on and you're not thinking about it. Well, what is that? Well, actually two things. Actually, we'll go through two things. One, you can't go from here to there without work being done on the system. Energy has to go into the system to go from here to there, okay? One. Second thing, remember, we had water in there. And that water, when it evaporates, boom, key word, evaporates, becomes water vapor. Water vapor, gas. Highly disorganized, gone out into the environment, gas. So we way more increased our disorder than we got order out of this thing. We way increased the disorder. Gas is so highly, highly disorganized. Remember those numbers earlier from the problems? How much greater gas values are for entropy than